it's on the hour, so I guess we'll get started. So our first presenter will be Zosia. So Dr. Zosia Staniaszec is an atmospheric chemist and a climate modeler currently working at CICERO. She has her master's and her PhD in chemistry from the University of Cambridge in the UK, and her PhD investigated climate and composition impacts of methane mitigation using the Earth System Model UK ESM, for the first time including a fully coupled methane cycle. Her research now covers many topics, all aimed towards understanding chemistry-climate interactions and feedback mechanisms. And so I'm very interested to hear what she has to say. And Zosia, whenever you're ready, you can go ahead and share your slides.
Yeah, thanks for the great introduction. I'm Zosia, and I'm currently working at CICERO, a climate research institute in Oslo. And some context for my background in atmospheric chemistry, and I'm talking mainly about interactive methane, which is the topic of my PhD, and the context of that is the move towards emissions-driven Earth system models in CMIP 7, so namely CO2 emissions and resolving the carbon cycle in that way. But also potentially later on with methane emissions as well, kind of after the fast track phase. So there's a lot of interest in this area at the moment, which is exciting. So just an introduction on what does concentration-driven model mean and what does an emissions-driven model mean. So these are the profiles of CO2 measurements and methane measurements over time. And in a concentration-driven model, you take these and put them into the model as a lower boundary condition. So we set what the CO2 is in the atmosphere or what the methane is in the atmosphere. And because these are long-lived in the atmosphere, so CO2 has a lifetime of over 100 years and methane is around 10. This is a reasonable approximation previously in models, but it does limit some of the processes that can be included, and especially the feedbacks that we can simulate. So this is a basic figure showing the carbon cycle. So what we're doing in a concentration-driven model is kind of taking all of this and saying what the amount of CO2 is in each year in the atmosphere, whereas the individual models, so like the land model or the ocean model, they do resolve these processes. They're just not all coupled together. So when we move to an emissions-driven model, we kind of have a more process-based understanding and a more process-based representation of what's happening. And for methane, there are various different sources. So from fossil fuel production, agriculture, there's biomass burning. There's also a very large natural component from wetlands and other natural emissions. And so we want to be able to resolve these in the model. And there are large uncertainties in these emissions. So we can do kind of a bottom-up approach where you sum all of the individual, cows or fields and wetlands and things, or a top-down approach where you look at the whole system and what makes sense in terms of the sources and sinks. And the main sink for methane in the atmosphere is by reaction with the hydroxyl radical OH, and then there's a small sink in soil as well. So how do we go about translating these emissions into concentrations? So first of all, in the concentration-driven model, we have our emissions from the inventories, and then use an external model, which is the same for, so all of the CMIP 6 models would use this process, where we use an external model, normally Magic C, and it has assumptions in there about the methane lifetime, the oxidative capacity of the atmosphere, so how quickly the methane will react, and also the other chemical state. And then we get a methane profile over time from that, and that's what we put into the model. And I'm speaking from a UKSM perspective, but it's broadly the same for all models. And then in that model, you have the chemistry, transport, and some limitations on what feedbacks you can include because the methane concentration is already set. Whereas when we look at an emissions-driven model, you have the same emissions, but you put them directly into the model, and there's the chemistry and transport and feedbacks all happen online, and you get a methane concentration output. And crucially as well, there's a feedback where what happens in the model can affect the methane concentrations and the methane emissions. For example, if you have online wetland emissions, so the wetland emissions in the model respond to temperature, CO2, maybe rainfall and wetland extent, that will then change the amount of methane emissions that come from those wetlands, and it will change the total amount of methane emissions and therefore the concentration that's in the model. So that means that we kind of can get a wider range of results for what the concentration is at the end, depending on what model you have and your parameterizations and the chemistry. But importantly, that uncertainty was already there before. We just weren't resolving it in the models. So this plot is actually from it's from an opinion paper talking about carbon emissions driven for CMIP 7. So it applies for CO2 as well. And this orange section is the kind of new uncertainty you can resolve when you have emissions driven scenarios, rather than having this kind of implicit emissions uncertainty in that concentration pathway that's not being resolved. So just a brief introduction to UKSM1, showing mainly results from that, and how we've edited it and what was added by colleagues at the Met Office to make this methane emissions scheme. So the main parts that we focus on are the atmosphere and then the land surface model. So the land surface model already has online wetlands there. They just weren't coupled into the atmosphere. So that coupling was one of the main parts of the process. Then one of the other main things was adding soil sink, kind of as a deposition term of methane coming out of the atmosphere. That's a small but very relevant part that needed to be added. And then, yeah, we have this methane emission scheme, which is now available in the next version of the model. So what happens when you have an emissions-driven model? So here's showing the methane concentrations over time for the historical period, with the concentration-driven results in orange, which are by design follow the observations very well. And then in blue is the emissions-driven model. And you can see there's a low bias, especially kind of after the 1920s and moving into the 2000s, it gets larger. And there's a question of how, why is this happening? So for one, there's a large uncertainty in the emissions that you put in. And then there's also kind of the processes that happen in the model. So the chemistry, a lot of models have too much OH, or it's very hard to, there's not a lot of observations on what we can compare to kind of validate that. So if the methane is getting too destroyed too quickly, that could also be a reason why it's low bias in this methane concentration. And of course, that then affects the results, for example, because the methane concentration will affect the amount of global warming that we have from that and the temperature impacts and air quality impacts. And then from a distribution perspective, so this is now showing the methane distribution over the from the South Pole on the left to the North Pole on the right, and then in orange is the concentration driven result. So yeah, we have one value for the whole of the globe, and in black is the observations from NOAA, and you can see that it isn't able to resolve this kind of north-south gradient, which happens because there's a lot more sources in the northern hemisphere compared to the southern hemisphere. So the emissions-driven model does capture some of this trend, this kind of distribution, but there is a low bias in the northern hemisphere, especially when there's close to these sources. And here the two y-axes are offset because of that low bias. So it's just kind of showing that we are able to resolve some of this latitudinal distribution in methane. And so there's different ways to kind of approach making the model better and tuning and adjusting it to get the concentration that we see in observations. So this is again showing the plot that I showed before on the top, and then on the bottom is the residual flux that you would need to make the emissions-driven concentration match the observations or match the concentration-driven one. So it's kind of like a methane emissions missing source that you would need to add to make it consistent. And it's around 0 in the pre-industrial period, and then increases to around 50 teragrams per year in the kind of more present day. And for context, the total emissions are about 500 to 600 teragrams, and the 50 teragrams is well within the uncertainties of the emissions inventories, which those uncertainties are quite large. And then just to show, there's a few other models as well that are able to run with methane emissions. One of them is GFDL, and this is a tuning approach where there's the initial emissions on the top, which are from the inventory, and then in the two lower panels, it's tuned. The emissions are tuned to the anthropogenic emissions and the wetland emissions, which in this case are an input to the model. They're tuned to better simulate the concentration. And yeah, so what do we get out and what can we do with it? So this is an example of an experiment where I removed all the anthropogenic methane emissions from 2015 onwards, and to kind of constrain the role of methane in the future in an SSP 370 scenario. And the main point I wanted to show from this plot is the blue line, where the methane concentration goes down much more rapidly than we expected, and goes down to below pre-industrial levels. And this is because of the feedback that's enabled by using the methane emissions, where you have less methane, which means there's less methane destroying OH, which is the main sink for methane in the atmosphere. And then you have this loop where then there's more OH and you can destroy more methane, which means there's then again less methane. So it kind of accelerates the decrease in methane. And I think this is really interesting for looking at mitigation scenarios and how there's a difference between a concentration-driven approach and a methane-driven approach when we look at emissions changes over time. And this is very model dependent. This is an example from the GISS model, who also have a methane emissions configuration, where on the left here in the blue line is for a concentration-driven model, the version, and then this is for kind of like a maximum technical feasible reduction of methane. And in the purple is the same emissions put in directly into the model. And you can see they can't achieve this methane decrease in that model. And the point of this is now that you have these results, because it's all process driven and all coupled in feedbacks and everything, you can kind of pick apart which processes are responsible for these changes, which I think leads to some exciting results. So for example, here you can see the methane lifetime increases in that scenario. So the methane stays in the atmosphere for longer, which means that it's harder to decrease the concentration. And this is another study showing strong methane mitigation from the UK Met Office. And in the colours, it's showing the change over time. So in red is pre-industrial, and then it goes into the future, where it's following an SSP 126 trajectory, which has strong mitigation. And here, the emissions on the x-axis and the burden, which is kind of similar to the concentration of methane in the atmosphere, kind of follows, they're proportional. So if you increase emissions, the concentration goes up, and then you decrease them again, it goes down again. But when we look at other variables, so on the top is the wetland emissions, and then on the bottom is the methane lifetime, which strongly affects the global warming impacts of methane. We don't return to the same state once you decrease the emissions. And this is for the wetland emissions particularly important, because in the future there's higher wetland emissions, whereas in a lot of models the wetland emissions and the biogenic emissions are assumed to be constant. We can see that's not the case when it's all coupled together. And then another opportunity that you have with the emissions driven is to change emissions heterogeneously in different regions. So here's an example of an experiment where kind of following a global methane pledge, which is a global 30% decrease, where the countries in darker green continue on the current trajectory, and then the lighter ones have a strong mitigation. And this wasn't possible to do before, when you just have to set the concentration globally. And you can see that this is now the change in the surface mixing ratio in methane, and this is very heterogeneous. And so there's interesting regional impacts that we can look at with the changing methane concentrations in different areas. And one of those is looking at the ozone impact. So methane is a precursor for ozone, and ozone is a strong air pollutant in many regions. And so this is showing them on the left is the methane average 8-hour daily average concentration. And then on the right is the number of days where that exceeds the WHO threshold for air quality. And then for like a global methane pledge, so a lower methane scenario. And you can see that the main point of these plots is just to show that there's a regional local impacts on air quality that we can resolve. So yeah, in summary, there's a new generation of these emissions-driven models, both for methane, which maybe is a later development, and then also for CO2, coming for CMIP and beyond, and that we need a more process-based understanding to implement this, but it also gives opportunities for more process-based analysis for the response, and we can answer kind of new questions looking at that. So that's all from me, and thanks for listening.
Thanks, Zosia. So if anyone has questions, feel free to raise your hand, or I'll be checking the Padlet as well. I thought it was very interesting, your statement that this uncertainty is already there in the before we put the emissions driven in. I think people going into CMIP 7 are very worried that we now are going to have a bigger range in our results because of the uncertainty of switching to emissions driven. But I liked your comment that that uncertainty was already there, it just wasn't previously resolved.
Yeah, I think it's you can have a lower uncertainty in theory, but you're kind of all using one model to convert from the emissions to concentrations, which obviously is a limitation of the previous method.
Okay, so I see a hand up from Annika. So if you're able to unmute, or you can write in the chat.
Yeah, perfect. Thanks very much. And no, it was very, very interesting. Thank you, Zosia. That's how you pronounce your name, I guess. It was really, really nice to listen to your talk, especially because I have a favor for methane and all the discussion. I was just wondering, thinking back of the research that I did a couple of years ago, where I also worked with the UKSM model, and especially I looked at the land surface model that is integrated with this, which is the Joules model, that I saw also permafrost is not yet part of this model. Do you know anything in that direction? Because I mean, this then influences again the trajectory of methane. Are you currently working on this, or sorry?
No, so I'm not currently working on it, and I know that there's not like interactive permafrost, or even that I don't think there's emissions from permafrost for methane in this model. Partly because they're very uncertain and difficult to parameterize, and that you just don't really have that information. And I know it's really not my area at all, but I know some other models do have it in there more. I think the numbers for the total budget for that are very low, but of course, maybe kind of in a tipping point discussion and thinking about that, they might increase in the future. So definitely something that's relevant for this topic, but not something that I know about very much.
Okay, thanks.
I might just jump in if it's all right, seeing this. But it was really interesting. I was just going to ask about the effect of like the feedbacks on the historical concentration, because you showed like a single member, right? Is there, what happens if you run like an ensemble? How much uncertainty is there in the present day concentration, based on like variations in the historical temperature from initial conditioned ensemble, compared to that error that you showed?
Yeah, so it's very low. Like there are actually 3 ensemble members, you just can't see them. So yeah, the concentration that you get out it's not dependent really on the internal variability. It's much more dependent on the emissions that you put in. So for this, you don't need many ensemble members to see what molecular concentration you get out.
Interesting, thanks.
Sorry, I just got kicked out of the meeting, but it seems like it's still going okay. Fanny, do you have a question? And then we'll move on to our next speaker.
Yes, thank you. Thank you. It was a great presentation. You showed that the emission-driven simulation gives out lower results than the concentration-driven one in the UK ESM model. I was wondering if you get consistent results across different models, or if some of them might give different results with higher, high on the higher spectrum.
Yeah, I'm not completely sure on how the different models get like pre-tuned their results, because often the kind of method of getting to an experiment ready version is different. So often the models will tune those emissions before kind of in an iterative process to get a better concentration. So yeah, I think the different modeling centers have different approaches to that. So I'm not sure whether they all underestimate it or what that looks like. And it's actually, there was a paper today from EMAX, which is another modeling center looking at their emissions-driven methane configuration. So it's very much like a ongoing area of research. So it's exciting. Yeah. Okay, so there's also a need for a more consistent procedure, like tuning this in protocol. I don't know if, yeah, I guess it's good to know or have a very clear what different modeling centers are doing on that. I don't know, you know, what the best approach is, and that kind of depends on the chemistry in your model and the processes and what methane concentrations you get out. Yeah.
Cool. Thank you so much, Zosia, for your nice presentation and discussion. If anyone has other questions, you can continue to write them in the Padlet, and we'll keep an eye on that. So next, I want to introduce our next speaker, Professor Joseph Mutemi. So he is a professor at the University of Nairobi in Kenya, where he also obtained his PhD. He's contributed extensively to understanding of weather patterns in Africa, including work on disaster risk reduction and sustainable development. His research has informed national and regional strategies on climate resilience, and also through his role in the GCRF African SWIFT project. He's well known for bridging science and policy and for his work on the development of multimodal ensemble forecasts for climate change assessments. So yeah, join me in welcoming Joseph, and when you're ready, feel free to share your slides.
Thank you for that generous introduction. That's me. I thank the organizers for this opportunity to give a short flashlight presentation, probably with one or two key messages. And I like really the whole title of this workshop, Fresh Eyes on CMIP. And I've shared my screen. Can I know that at least you see some of my computer, and then you can actually see the brief presentation?
Yes, it's not in presentation mode, but we see the presentation.
Yeah, sure. Now it should be in presentation mode.
Great.
And so basically, I followed I was in another activity, so I just joined the last 10 minutes or so. Thank you, Zosia, for excellent talk. I think it kind of seamlessly connects basically with what I'm going to be highlighting, as of course entry points for you and also the upcoming early careers in climate science. What impactful research you can be working on, which actually will inform sensitive societal decisions on coping and of course adapting and mitigation, and at these times when climate either change or variability and emerging changes, and then uncertainties in projections, keep us very busy in our work. So because I've been one of my recent contributions was in the physical science basis of the group 1 work, and of course the consequent report, which I'm sure you have engaged in, and also have engaged in, and I don't say even at this point we have exhausted what we need to learn out of the current modeling level and the skills and knowledge and the data sets and what you need to do. But just to put things more in perspective, we need to be informed by many attributes of our current knowledge as to where else do we need to go, where else do we need the climate science in the model developments and the modeling centers and early careers you need to go. And I think this pictorial, which actually is directly from chapter 4, continues to be very good, and I think we all know it, and it is it still delivers quite strongly and with good evidence of the not just the current knowledge and the foundations of global temperature, or even you go to the regional chapters and you can also get similar trends. But very importantly, that still we are at a level where models quite well. Actually, way back in the before the start of this current decade, well anticipated the current extremes we are witnessing worldwide, or even in Africa in particular, and even East Africa, where I operate from, and Kenya in particular, and those extremes continuing to be quite a concern. And like you see the instructed insert graphic, just this I think this purple here is the initialized predictions from the decadal experiment, and I think that is very good. And actually, when you look at how the ensembles, I think which are actually colored in light blue here, did on the same, you see, of course, are quite a convincing, indication that the models are currently up to the knowledge we had and the literature which we had, which informed the policy directions coming out of the SIG assessment are quite good, and I think that is continues to be the case. And just to put this more in perspective, I wanted to highlight in this particular workshop what of course what is informing these in terms of where are the impacts and what is the status. And I think it's good to always remind ourselves, actually, since the last century, 1900s, and now we are almost in the early stages of this current century, and each decade globally, actually, almost every time hitting records in terms of successive global warming. Last year is still happened to have come out, top globally, and you look at the left panel, the right panel, this one, which actually is Africa status. It is still the same, and of course these results, whether we generate them, and of course they are well backed up by literature and of course what is done, but they can also be dependent on several factors. For example, on data sets which are available and which are good quality to inform these can actually give slightly different results. And this is I think it continues to be a good engagement of those who are working on data assimilation or development of data sets, whether they are global, whether they are the climate research unit data sets, or era 5, or MIR, or those who use reanalysis data sets from the Americas. They can actually give a slightly different resource, but overall, I think the indication is the same. So, for example, this particular product which you see here, we generated it just about 2 months ago, so that we can continue to provide the current status of the African continent, which actually informs the high-level programs. For example, what the WMO is urging in terms of embassies or policies, and information which feeds into continental-wide flagship projects like early warning for all and these kind of things, and then of course the indication is that we are still deep in the woods when it comes to actually climate change and global warming at regional and even at local level. And these details happen to be very, very important. In fact, because I said it's just going to be a flashy presentation, I picked this particular detail from our Africa status, which we are now just starting to bring to attention of researchers, and it speaks for itself. And this presentation, actually, you can share it just the way I sent it yesterday for other careers to pick details and identify what they can also add into their research. And you see, of course, regional details. I come from East Africa, actually, which is colored in blue in this, and you can see that except of course for the slight dip in the 1930s to 60s, and the rest up to present continues to be quite an issue, of course. Thankfully, of course, here in East Africa, we do not suffer heat stress, as you see actually in the northern sector of Africa, which is okay. But when it comes to these impacts, then the capability to be able to actually work and bring out really local scale details are very important, because we are at a phase where planners of climate sensitive infrastructures or services, be they clean energy like enhancing hydro or wind power and these kind of things, details are very important. For example, you can actually you don't even see in this where do we, for example, put important resources like like the wind power in this, because East Africa and like details like the jets, which are very important for this, are actually relevant. So even though the resource generally will very much be okay for us, we know that we have to work on the particular details which continue to inform area specific attributes of both the weather and the climate science. And this is something now which as a champion, I need to point our early careers to. And in fact, and just to start moving towards the end, and I will allow me, as I said, to just remain in our highlights from our IPCC work. I picked a presentation, and this actually the way we put it in the synthesis report for policy making, and again it speaks for itself. And when I was thinking about this, what to talk about in this to early career, this one kind of I said I'll use it, because when you look everywhere on the globe, it's only Northern Europe, for example, where you see the high confidence in the projected change of heavy precipitation. And of course, early careers will be interested in asking, of course, what is it that modules do much best over there than over the rest of the world, actually, where you see it is all medium confidence. of course, when you go to areas where there is limited data sets or even literature, as you can see, over most of my region is actually there. Also, highlands are also there, because you can see the island of Madagascar, and of course, basically most of Africa, where we have to pull our socks in terms of literature, in terms of quality data sets, and then bringing the obvious entry point that this should not be the situation. So while we are happy that modeling has come this far, and we are able to provide the highlights we have given, and using the calibrated IPCC language, we have this as the strongest possible evidence. We know there are limitations, and there are actually details. And maybe I will just remain on this slide to make my final remark. And I'm sure following even the last speaker, those of us then who have the opportunity to be working in modeling centers, informed by this, of course, you can just confirm this result with the most recent configuration of your modeling system, or be they in data assimilation systems. But most importantly, of course, where almost everywhere it is low, limited agreement between models, and the models actually don't sit to make agreements like human beings. Models do what they are supposed to, what they are configured to do, and what they are populated to do. And actually, there can be quite excellent impacts if at least as you put your fresh eyes on the next, on the next CMIP experiments, and what modeling needs to be done, at least in the next few decades, you'll have actually pulled out of this kind of list your model out of it, or you would have increased, of course, the confidence. Will have done quite useful work in terms of modeling and advancement, so that we can have increase in the degree, actually in the next level of climate advancement, which informs resilience building, and actually challenges both at regional and even at local level. So I want to exit by just saying that it is true, a lot has been achieved, a lot actually has to be done, and that can only be entrusted onto the early careers. And again, coming back to this slide to make just my final remark, do not actually aspire to work on all models, but you can actually work on one model and keep any other model which is at your fingertips as a control, and actually you will make a quite a significant contribution, which actually will be informing strategic, high level, policy decision, and making products like, the next generation cycles of, global climate decision for, for resilience building, and of course, climateness smart in the world. So I'm grateful to the organizers of this exciting, forum for early careers, and I am sure maybe this has, increased the orientation and the motivation of, at least some of you. Thank you very much. Was I audible?
Thank you. And I think that was a morale booster in terms of that there's still lots that needs researching and there's lots of opportunities for us as ECRs. If anyone has a question, I think we have time to take a question. So raise your hand or put something in Padlet. Okay, I see a hand from Helene.
Thanks for that. I'm not an early careers scientist, but I'm interested. You showed the pictures from the state of the climate for Africa. So do you think is that a good place for people to get involved as well?
Excellent, Ellen. That is yeah. Actually, and to be able to complete those results, which actually we are putting in that report, there is a minimum. There is a little bit of Africa's specific data from the Met services, but in terms of quality and harmony with the global climate, we actually have to work with global centers. In other words, it would be quite a good input that when we are doing this report starting from the end of this year, when we are preparing highlights for the next COP, and of course the status for 2017, we have gotten any inputs from this forum and other climate forums. And so you are very welcome actually to be in my team, which actually is working on this through and this is what also we are encouraging, that in climate science, we do not increase and strengthen our partnerships and the sources of information, which actually informs our synthesis, statements, which now go to the high level. We do not achieve much. So excellent opportunity for all to increase our partnerships in this. Thank you very much.
Thanks.
Thank you. I think just to keep on time, we will move on to our next speaker, but continue to write in the Padlet if you have more questions. As you can tell, Joseph is very experienced. So if you have more general questions about working in research, etc., I'm sure he'd be very happy to answer those too.
Thank you. I will remain connected for another maybe 30 minutes or so. Thank you.
Thank you. Okay, so we'll move on to our next speaker, which is Dr. Doug Smith. So Doug leads the decadal climate prediction team at the Met Office in the UK. And since completing his PhD at Imperial College London, his research has taken him to many institutions across the UK until joining the Met Office. His research now focuses on monthly to decadal prediction, variability, and forecast skill. And he's also been involved in several of the CMIP MIPs and is currently involved with the Forcings task team. So Doug, I can already see your screen, so feel free to start when you're ready.
Great. Okay, thanks for the invitation to talk today. So I'm going to talk about something that I'm quite passionate about, and that's the need to account for model error in prediction and attribution. So I'm going to start with this slide that shows two very different model projections from the same climate model with only bit level perturbations to the initial conditions. And these opposite trends that we're seeing over Europe suggest that, at least in this climate model, there's irreducible uncertainty due to unpredictable internal variability. Now, if this is true for the real world, then we will never be able to make confident projections for Europe and actually for many other parts of the world. So, and if we look at decadal predictions, we would arrive at the same conclusion, actually. So what I'm showing here is 8-year running mean prediction. So the observations are in black. We have a large ensemble of decadal predictions. The ensemble mean is this red line, which doesn't show very much variability at all. And we can find ensemble members just as in the previous slide. So some of them ensemble members actually look quite similar to the observations, whereas other ones have the opposite signal. So if we take the model at face value, this also suggests that there is irreducible internal variability and that we don't have any skill in these projections or predictions. But this can be tested So the plot on the left here shows the same as in the last slide, but on the right you can see that actually there is quite a high correlation between the observations and the ensemble mean of the decadal predictions. And here I've adjusted the variance to bring that out that correlation. So a correlation of 0.79 should explain 62% of the observed variability. But if you look at the left-hand slide, then clearly the ensemble mean explains very little of the observed variability. So there is an inconsistency between the very high correlation and the amount of variability that can be explained. So this has been noticed before. It was first noticed in seasonal predictions of the North Atlantic Oscillation, the NAO, and we called it the signal to noise paradox. And I'll explain what we mean by that. So the black line here shows the correlation between the model ensemble mean and the observations, and you can see that rises steadily as we add more ensemble members. So the x-axis is a number of ensemble members going into the ensemble mean. So that's expected, but what's not expected is this blue curve down the bottom here, which is the model predicting one of its own members that's been withheld from the ensemble mean. And what you can see here is that the model skill at predicting its own members is much less than the skill for predicting the real world. And this is a paradox because you might expect the model to predict one of its own members with higher skill than predicting the real world because it perfectly represents itself. So what we conclude from this is that members are not alternate realizations of the observations. We also need very large ensembles to extract the predictable signal. And this kind of undermines the basis of ensembles, I think. So what's going on here? So in this upper plot, so what I'm showing is the total variability in black and the predictable fraction of that variability in red. And what we can see is that the predictable fraction is much bigger in the observations than it is in the model. And we can actually measure this error by the RPC, the ratio of predictable components. So that's simply the predictable component in the observations, which is related to the correlation between the model ensemble mean and the real world forecasts or real world observations. And the predictable component in the models is simply the variability of the ensemble mean divided by the total variability of the ensemble members. And if we take that ratio, then if everything is okay, this RPC should be 1. And any RPC that's greater than 1 shows the signal to noise error that we've been talking about. And note that this error is not seen if you just look at the total variability, because the black bars in these two cases between the observations and the models is exactly the same. And so this is a real issue in decadal predictions, at least. So what I'm showing here is the skill for predicting sea level pressure years 2 to 9 in decadal predictions, multi-model average decadal predictions. And then on the right, I'm showing this RPC measure, which measures the magnitude of the signal or the signal to noise error. And what you can see from this is that wherever we have skill in decadal predictions of sea level pressure, atmospheric circulation, we also have this signal to noise error. So, it really does dominate at least decadal predictions. So now I'm going to move on to projections. Oh, don't know why it's doing that. Anyway, so what I'm showing here is this paper from Blackpool, Port and Fife, which shows trends from 1951 to 2020 in upper or U200 winds in the upper panel, and rainfall in the right-hand panels, compared with the multi-model ensemble mean from the CMIP 6 predictions. Come on. And these okay, and these crosses show where none of the ensemble members, and there are more than 300 of them, simulate the observed magnitude of the changes.
Sorry, Doug. Not sure if it's just me, but I can no longer see your screen.
Oh, really? Sorry. That's weird, isn't it?
Maybe you can stop share and share again and see if... Oh yeah, okay, it's coming.
Yeah, is that right?
Great, okay.
Can you see that?
Yeah, it looks good, thanks.
Okay. I don't know why it's doing this. I've obviously recorded something and it's playing that recording, sorry. Okay. So basically there's a discrepancy. The potential signal to noise error in the simulation of U200 winds, zonal winds. Okay. But it's not quite as simple as just taking the multi-model ensemble mean and diagnosing the signal to noise error like we did with decadal predictions, because the models, what this slide is showing is that the models can be completely different, so even have opposite responses to the same forcing. So this is again the NEO, and this is 31-year running means. So the observations are in black, and the ensemble mean of selected models, as shown by the colored lines. Can you still see that?
Yeah.
Okay, great. Okay, but what you can see is that in the future projections, there's a full range of uncertainties. So some of them show an increase in the NEO, some of them show a decrease, and some of them show little change. And two of the models are significantly correlated with the observations over the historical period, but they also show very different projections. So why is that? So what I'm showing here is the regression between Earth's energy imbalance, EEI, and zonal mean zonal wind for two selected models that actually show opposite responses. So CANI-SM5 shows a poleward shift of the winds when there is a positive energy imbalance, whereas CNRM shows an equatorward shift of the winds when there's a positive energy imbalance. So fundamentally different, opposite responses in these two models. So why is that? So what I'm showing here is the same thing, but now with zonal mean, so the narrow correlation between Earth's energy imbalance and zonal mean temperature. And what you can see is that when we have a positive energy imbalance, we have a warming of the troposphere and a cooling in the stratosphere, and that generates a gradient, a meridional temperature gradient at particularly at 200 hectopascals, that would be expected to shift the winds. But where this gradient occurs in these two models is fundamentally different, actually. So, and this explains why CANI-SM5 shows a poleward shift and CNRM shows an equatorward shift, because that gradient is on the equatorward side of the jet, whereas in CANI-SM5 it's on the poleward side of the jet. So this magenta blob is the jet latitude. And so to understand why that is, so what the difference between one major difference between the troposphere and stratosphere is water vapor. So there's very little water vapor in the stratosphere. So what I'm plotting here in this green blob is the hydropause latitude, so the change between the troposphere and stratosphere, diagnosed by a water vapor contour. And what you can see is that in Canny SM5, this hydropause latitude is poleward of the jet, whereas in CNRM, it's equatorward of the jet, and that's consistent with the opposite responses in the winds. So this potentially allows a constraint to be derived, which would be effectively a weighted sum of the models. So if we just look at the so in that way we can potentially exploit these model differences. So if we look at the if we take the models at face value, then over the historical period, there's very little correlation between the multi-model ensemble mean and the observation. So it's not significant at all. And this suggests that there's not an externally forced response in the decadal variability. But we get a very different conclusion if we use this constrained time series based on the hydropause latitude relative to the jet in all the models. And now we have a high correlation with the obs over the historical period, suggesting that decadal variability is externally forced to some degree at least. But also we also find that this is subject to the signal-to-noise paradox that I mentioned before, and we have to scale this this constrained time series by 4 times to match the observed the observations and therefore get reliable predictions and projections. Okay, so just to summarize then, wherever we see skill in decadal predictions of atmospheric circulation, the signals are too weak. This means we need very large ensembles to extract the predictable signals. We also need to boost the ensemble mean signal. And this also appears to be true for climate projections. Models show very different, even opposite responses to the same forcings. They definitely can't all be right. So we need to do something to take account of those differences. And if we do account for those model differences, at least for the NEO, that reveals externally forced decadal variability. And this is missed if the models are taken at face value. And you know, a key message here is that taking models at face value could leave society unprepared for impending extremes, because as I showed in the previous slide, the projected changes in the constrained ensemble are far higher than in the unconstrained ensemble. Okay, I'll leave it there.
Thanks, Doug. And sorry to interrupt you partway through.
No worries.
We do have a bit of a buffer time, so if you're happy to stay online, we can take some questions. So anyone in the audience, feel free to raise your hand. I see Julia already has a hand up.
Hi, Doug. Thank you for that great talk. So I have a question more related to how this could be extended to other problems, because as the way I understand it, you identify this emergent constraint, and I understand that you weight your models based on this bias in the relative position of the jet. But I imagine that this particular way of weighting the models might not be, for example, the same if we want to extract this predictable signal in the southern hemisphere or for other processes. So yeah, what are your thoughts on how do we identify the correct constraint or a correct way to weight models depending on the process that we want to provide projections for?
Yeah, good question. So identifying the constraint is the difficult bit. I think it's a matter of understanding what could be driving the variability that you're interested in. And for the NAO, it's kind of the shifts in the winds, that are strongly related to the NAO. So a positive NAO is a northward shift of the jet, and the opposite for a negative NAO. So it's understanding what could be driving those shifts in the winds. And I'm interested actually to look at the Southern Hemisphere to see if, the same constraint might apply there as well, actually. But for other things, like the discrepancy between the models, simulation in the Pacific, for example, it's very difficult to understand what's causing that. But I think again the models are different to some degree, although they all agree on a kind of El Nino type response. There are some differences that could potentially be exploited to understand that this discrepancy as well.
Thank you.
Thanks. Any other hands up? Okay, maybe I can ask a question. The signal to noise paradox confuses me every time, and I always think I understand it in the presentation, and then afterwards I'm lost. But I heard recently that machine learned models also seem to be exhibiting the signal to noise paradox.
Yes.
Does that make any sense to you?
Well, we were very surprised about that, I have to say. So at face value, it would suggest that it could arise simply because there is some internal variability in the observations that happens to match the predictable signal, which, if that's the case, then it would suggest that it's actually not robust. But if you look at the forecasts that have been made since the signal to noise paradox was discovered, then these real-time forecasts also suffer from exactly the same error, and these would be an independent set of observations. So that would suggest that it is robust. But at the moment, we don't understand the reason for that. Sorry. Good question, though.
Okay, I still don't see any extra hands in the chat. I wonder if I can ask a question both to you and Professor Mutemi more generally about you guys have much more experience than us as ECRs, but in terms of how do we reach some of these areas? So for example, Joseph was showing a lot of areas in Africa and South America that have lots of high uncertainty. How does something like CMIP communicate with people in those areas and get them involved in solving some of these uncertainties?
Okay, so for me, Joseph might have a different answer, but for me, as I highlighted, taking into account model errors and differences is key, because if they are different, then they can't all be right for sure. And understanding what could be causing those differences provides an opportunity to constrain or narrow the uncertainties in the projections. So I really would encourage people to assess the model differences. I don't know if Joseph has got a different answer.
Sure, I will not differ. I 100% concur. My camera seems to be having an issue. Can you just know that I see whether you are getting me? Excellent. Thank you very much. And so basically, it is very important to catalyze and refresh the energy of the current early careers. Actually, not just in the regions, because you may find that, for example, we take an example of East Africa. I have so many of those kind of things to be worked on, but I don't have I don't have a good pool of early careers. Maybe our institutions don't have sufficient research grants, and when I write a proposal here and there, maybe it is just supports one fellow who works on one attribute and not the others. But climate science, we have to be quite holistic. So interesting those policymakers with the products like I showed in the group, in the economic groups, and also under the framework of international cooperation for common good. I think we can get things done well, because obviously, like focus work on looking at confection modeling and schemes. Central Africa and Amazon and all that requires quite a good amount of concentration, and of course a good PhD or even good postdocs who actually translate this information into operational work and what can be done to advance products. And I think these are the ways to go. So I think these things continue to highlight that while we can appreciate that we have done quite a lot globally and sometimes even in particular regions, there is still quite a lot which has to be done, and we are grateful that nowadays, at least AI and tools for data processing and lenses for turning in data sets upside down, and of course then working on uniformity principles of guided advancement in terms of what to do to reduce the uncertainties. And just as I indicated, at least if we can have researchers at least in dedicated careers or careers who work on a cutting edge, let us redefine the scale of the process, for example, because those are those traditional concepts which we found in the science. One just to kind of step on so that we can make the next levels. So I think there is quite a lot to do, and there is a good opportunity for all of us champions and also early careers to continue orienting our thoughts into what else we can do. We need to do. Thank you very much, actually, for those excellent results from the initialized predictions. They keep being our only source of informing policymakers that although climate projections for the next century are a model, but at least in the medium term, in the near term, we are there, and as we advance, we can still be able to show that these are actually good, and they are informing cyclone instances in our region, or storms, and influences of extratropics versus tropical interactions and things like this. And then we of course go to all the scales which matter, right from weather to long term. Thank you very much. So just remarks to keep us thinking about these things.
Thank you to all of our speakers today, and for everyone for asking questions and joining in the discussion.